Good evening, participants. Good evening, resource person. First of all, on behalf of our New Horizon College of Engineering, we are gladly to welcome all the participants and resource person for this IEEE sponsored international webinar on controlling megawatts with power electronics by the resource person, Dr. Tobias Geyer from ABB Medium Voltage Drives and ETH Zurich and Stellenbosch University, Switzerland. And this talk provides an introduction to high power electronics, reviews its control challenges, and proposes model predictive control methods to address them. For large electrical machines which is used in wind turbines, these control methods which will be increase the power and control power and their availability. So to achieve the task, so we are organizing this program, and I'm very happy to introduce here today guest speaker, Dr. Tobias Geyer. Dr. Tobias Geyer received his diploma engineering and PhD degree in electrical engineering from ETH Zurich, Switzerland in the year 2000 and 2005, and the habilitation degree in power electronics from ETH Zurich, Switzerland in the year 2017. After his PhD, he spent 3 years of GE Global Research, Munich, Germany, 3 years at the University of Auckland, New Zealand, and 8 years at ABB Corporate Research Center, Baden-Württemberg, Switzerland. There in 2016, he became a senior principal scientist for power conversion control. He is appointed as an extraordinary professor at Stellenbosch University, South Africa, from 2017 to 2023. In the year 2020, he joined ABB's medium voltage drives business as R&D platform manager of ACS 6000/6080. He is an author of 35 patent families and the book Model Predictive Control of High Power Converters and Industrial Drives, which is published by John Wiley in the year 2016. He teaches regular courses on model predictive control at ETH Zurich. His research interest includes medium voltage and low voltage drives, utility scale power converters, optimized pulse pattern, and model predictive control. Sir, on behalf of our New Horizon College, India, I am glad warmly welcome you for this international webinar, sir. Now we can start your lecture. Thank you.
Thank you very much, Professor Vinod Kumar. I'm very honored to be able to talk to you today. I count here more than 70 participants, so that's really a lot. So thank you very much. So I'm sort of a hybrid between someone who is in industry and someone who is in academia. I'm probably somewhere in between, maybe I'm in both. So during the day, I usually work for industry. So in this case, for medium voltage drives, but evenings and weekends, I mostly do academic work. So I have PhD students and I do lecturing, and I'm interested in the more long-reaching concepts that are maybe not directly applicable necessarily. So let's jump right into the topic. I want to give you a little bit of an introduction into power electronics and then talk more about control. So let's assume you have a photovoltaic cell on your rooftop and you want to connect it to the grid. So the photovoltaic cell, the PV cells, they produce a DC current, so a constant current over time, but the grid is AC, so alternating currents. So we need some interface in between these two worlds. So we need a DC to AC power conversion. And this can be done with a switching converter that transfers the power from DC to AC. Now, if you assume on the left-hand side, let's say 2 cells that have a total DC link voltage of VDC, and on the right-hand side, you have your grid voltage, 50 Hertz, 60 Hertz. You might have a grid impedance. That could be your distribution transformers and maybe your transmission transformers. And then you want to control this current. And the currents that we feed into the grid ideally is in phase with the grid voltage. So we get power factor 1, and we maximize the active power we transfer, and we minimize the reactive power. Now in between, we need this inverter. And in the simplest case, what you could do is you could just use two switches, an upper switch and a lower switch. Now, these two switches are meant to control at the terminal of the converter a desired inverter output voltage. And this voltage would drive the current into the grid and against the grid voltage. So this could be the voltage at your point of common coupling. Now, if you start switching, and for example, you might close the upper switch and have the lower one open, then the voltage you apply at your converter terminals would be half of the positive DC link voltage. And that means that you have a positive voltage across the inductor. So you will change the current and you will increase it. So the change in the current is proportional to the voltage across the inductor. And as this voltage difference is positive, you will increase the current. And that's what's shown here. So current will flow from the upper DC link rail into the grid, represented by the inductor and the grid voltage. Now, at some point, the current will be a little bit too high, and you will choose to turn off the upper switch and to turn on the lower switch. And if you do that, you invert the output voltage. It's now well below the grid voltage. And as a result, the current will reduce. Again, this will be more or less a constant slope if you assume that your voltage is constant in the short term. Now, if you do that repeatedly, if you turn on and off the upper and lower switches, you will get this distinctive current ripple, and you're able to follow your current reference. So star means it's a current reference. So switching approximates the sinusoidal waveform. So this dashed dotted line would be your fundamental component at the output voltage, and the stepwise function would be a switching function. Now, we don't have ideal switches. We have real semiconductor switches. Think of insulated gate bipolar transistors. They can feed the current only in one direction. And if the current is to flow in the other direction, we need these so-called freewheeling diodes. And if you now close the upper IGBT, you will get the current flowing through it. You have a relatively high current, but you also get this forward voltage drop. So there's an on-state voltage of a few volts. And as a result, we have conduction losses. So the losses in the semiconductor are simply the voltage drop times the current it carries. So there's a bit of an on-state loss. Now, if you want to turn off the upper switch and turn on the lower one, you will start increasing the voltage across the upper switch. And that will push the current from the upper switch to the lower diode in this case. So once the voltage comes up, you will start compensating the current away. But that doesn't happen instantaneously because the transient of the voltage is not instantaneously. It takes a couple of 100 nanoseconds, maybe a fraction of a microsecond. And during that time, the product between voltage and current is certainly not zero. You get these distinctive switching losses. And if then the lower switch is conducting, so in this case the diode, then the upper switch blocks the voltage. So the voltage you see across the switch is the total DC link voltage, VDC, and there is no current flowing through. So when you block, no losses. So these switching losses, they increase with the switching frequency and with the current you carry, and they in effect limit the current carrying capability, particularly of high power switches. Obviously also the on-state losses limit the capability. So we would like to switch as often as possible to get this current ripple low, but we are limited by the switching losses. Now you have this fundamental component in your current, That's what you're after. So this transfers real power, that's the desired quantity. And then you have this ripple component on top, which produces losses. So it disturbs the grid connected loads and it heats up your loads. So it's a bit like this, beer. You have this fundamental component you're interested in, but you get this foam on top that is a nuisance and that you would like to minimize. So we generally try to keep the ripple as small as possible. Now you can go for a low switching frequency. So that means you get a relatively high current ripple, or you go for the other extreme. That means you go for very high switching frequency and a low current ripple. So this means there is a trade-off. So if you start now plotting the harmonic distortions or the magnitude of the current ripple on the y-axis, and on the x-axis you put the switching frequency, and I'm jumping here from low voltage to medium voltage, where the switching frequencies are much lower and the distortions are maybe a little bit higher. You have these two extreme points: high distortions and low switching frequency, low distortions, high switching frequency. And what you see is that if you take one, let's say 8% distortions, 150 Hertz switching frequency, and you double your switching frequency, you get around 4% distortions. So the product between the two, the product between distortions and switching frequency is actually a constant with some mild assumptions. So we usually work along this trade-off curve. And then power electronics people, when they talk about optimizing, they talk about finding a sweet spot along that curve. But what optimizing, I would think, really means is you want to shift this curve closer to the origin. You want to find ways to modulate, ways to switch, in which you bring that trade-off curve closer to the origin. So you either reduce current distortions or switching frequency or both. But you don't want to trade in one for the other. You don't want to reduce one at the expense of increasing another quantity. Now, that's an introduction to two-level converters and to single-phase power electronics. In general, we have three-phase systems, and we might have more switching levels. So here on the left-hand side, you still have a DC link, an upper half and the lower half, which is still a DC quantity. But the converter now in each phase can produce 3 voltage levels, 0, plus, and -1. And you can see that you can now, it looks much more intuitive, the approximation of your fundamental component. Looking at that, you can imagine that with this discrete switching, you can now start to approximate the sinusoidal waveform. And we have 3 phases. So we have a phase A, a phase B, and phase C connected to a 3-phase load or a 3-phase grid. So R is the ohmic resistance. That's typically small. You can almost neglect it. And L would be an inductive component we almost always have. And your objective is to drive these 3-phase currents. And the beauty of a 3-phase system is that at any moment in time, you have constant power. So you can draw constant power from your DC link, and you don't get a power fluctuation. In single phase, you have a strong second harmonic. So that's sort of an introduction into power electronics, what it is. And now let's see what sort of applications we have. And then look a little bit into control and modulation, more generally. And then more specifically into model predictive control of optimized pulse patterns. And then towards the end of this talk, I would like to talk about an emerging topic. These are converter-dominated power systems, where the converters dominate the grid. And then to wrap up with conclusions and a bit of an outlook. And then we can have discussion. But let's start to look into applications. You had a question?
No, sir. No, sir. You can continue, sir.
No, probably no question. Then I will continue. So if you have a grid connected machine, so a direct online machine directly connected to the grid via a step down transformer, this machine is connected to a 50 Hertz grid, so it will produce a mechanical speed at the shaft that is proportional to the frequency of the grid voltage. So this will be, let's say, 3,000 rounds per minute. And with that, you can drive a mechanical load. So you get this electrical to mechanical power conversion. But if you would like to control the speed of your load, then you need to decouple the machine electrically from the grid. And you do this by adding a variable speed drive. So you go from 50 Hertz, from AC to DC with a rectifier. It could be a passive rectifier like a direct front end, or an active rectifier using semiconductor switches. And then you go from DC to AC, but now you can choose your fundamental frequency. And maybe you can set it in a range of 0 to 100 Hertz, maybe also slightly higher. So this gives you variable speed operation. But you could also then control your mechanical load very dynamically by very quickly adjusting the machine currents. And by doing that, you can achieve very, very fast torque responses in the range of a few milliseconds of your machine, and that can very accurately and very quickly drive your mechanical load. So for example, accelerating your machine without load from standstill to nominal speed, that could take less than a second if it's extremely fast. So these are variable speed drives, and an example would be a medium voltage variable speed drive. Medium voltage means we're talking about voltages above 1 kilovolt, 1000 volt, and below 35,000 volt. And this would be a 9 megavolt ampere frame with an output voltage of 3.3 kilovolt, around 6 meters long, 2.5 meters tall, a meter deep, and weighs 6.5 metric tons. And it's highly modular. It's a bit like Lego. I mean, you have here your active rectifier unit with a certain current carrying capability, your control unit, the inverter unit going from DC to AC, the DC link capacitors. This is here a small braking chopper, something that removes the voltage spikes in your DC link, and then the water cooling unit. Then you have here your active semiconductors. They're put here on a stack. Those are so-called integrated gate commutated thyristors. So thyristors you can turn off, IGCTs. They're put in this stack and pressed together. So these are press pack devices. One of these columns are the IGCTs, and the other columns are these diodes. We remember that we had these freewheeling diodes we need, or anti-parallel diodes. And these devices are water cooled. You see here the water pipes. And this is required because they get extremely and very, very quickly, very, very hot. So one needs to actively pump quite a bit of water through them, deionized water, to remove the heat. Now, nice application of such a drive would be ships, large cruise ships in particular. And what is done there is the propulsion system is in the ship. So we will have here the diesel generators, the switchboard, transformers, and the variable speed drives. But the motors, the electric motors, they are put in pods that hang below the hull of the vessel. So the synchronous machines are in here, and they drive these big propellers. And in this ship, we have 3 of them, the 3 large propellers. You see here the stern of the vessel. Things are turned here. The bow would be here in front. At the time, this was the largest cruise ship in 2009, the Oasis of the Seas. And it has a propulsion system of 3 times 20 megawatt. And for cruise ships, this is the state of the art. One reason is to reduce fuel consumption. You don't need a rudder. I mean, you turn these pods to get the thrust in the desired direction, so you don't need the rudder. But you can also decouple the mechanical speed of the diesel generators from the propeller speed. So it's a bit like a diesel electric train engine, where you can then operate your diesel generator at its point or rotational speed of the highest efficiency, independent of your propeller speed. And you get very good maneuverability. I mean, even at standstill, you can get the thrust in any direction. So this is state of the art, and you also get a high degree of redundancy. You have 3 independent systems, and each synchronous machine actually typically has 2 sets of 3-phase stator windings with 2 independent drives. So it's a full redundant drive. Now, looking more generally into power electronics applications, and if you look into the high power and the high voltage, and let's look at the grid. I mean, extra high voltage, 220, 380 kilovolt, or high voltage. What you have there is high voltage direct current transmission lines, so HVDC. So you transmit bulk power over hundreds, maybe even thousands of kilometers, maybe up to 8 or 10 gigawatt. You can do the same, but with a back-to-back coupling. So just a few meters in between, for example, when you want to connect a 50 hertz with a 60 hertz grid, or you want to decouple 2 grids. Then we have static synchronous compensators. They're also power electronics. We have railway interties. We connect a 3-phase AC 50 hertz system to a single phase, maybe 16 2/3 hertz grid. And then we have offshore wind feeding into that system. So at the time, those were 5 megawatt wind turbines. Nowadays, we have 12 megawatt plus for offshore wind. The development is moving towards 16, 17 megawatt. In the more medium voltage, mid-power range, so 10 to 35 kilovolt is medium volt, 1 to 35 kilovolt is medium voltage. We have still the static synchronous compensators, but we now have medium voltage drives. We have regional power generation. Think of land-based wind turbines, photovoltaic cells, and so on. And then there is low voltage. So that's typically 400 volt, maybe 690 volt. And this is more the world we are familiar with. You know, consumer electronics, power supplies for personal computers or screens or chargers or lights, LED lights, all these different home appliances. I mean, they all use power electronics. Then we have lifts, conveyors, cranes, but also industrial automation. So robotics, things that move, things that are driven. I mean, there are lots and lots of small drives. And then there's transportation. So electric vehicles where you have a battery and you need the power conversion stage between the battery and the machine, the traction motor. The same applies to trains. So they're typically diesel electrics, or you have diesel generator that produces electric power that is then fed to the traction machine, or this example of large cruise ships or large icebreakers using diesel electric propulsion. Now, let's look a little bit at the market and how things are evolving over time. I mean, this is old data. It's 6 years old now, but the projection was made for 2020. And you see on the left-hand side, the growth rate per year. And on the x-axis, you see the inverter switching frequency divided by the fundamental frequency. So that means how often do you switch per waveform. And a huge emerging market with a huge growth rate is electric vehicle traction, so electric vehicles. So estimated at around 600 gigawatts per year, but at relatively low power. So, but they don't switch very often because the fundamental frequency is relatively high and the switching frequency is quite low. Then there's electric vehicle charging. So the infrastructure to supply power to the vehicles, that's around 200 gigawatt, but switching frequencies are much higher. We would be looking at 5 to 10 kilohertz at 50 hertz. Then there are low voltage drives. So that's a classic domain, but it has modest growth rates because it's an established field. We have photovoltaics, nicely growing. We have onshore wind, not that much of a growth, uninterruptible power supplies. So these are more the traditional segments. We have battery energy storage systems, very small, but predicted to be a very, very high growth rate. Then railway traction, so locomotives, an old and established field, a sizable field with 100 gigawatt, also very, very low switching frequencies per fundamental frequency. Medium voltage drives are relatively big as well. They also have a very modest growth rate because it's an established application. And then there's high voltage DC, pump storage and static synchronous compensators. And these numbers are gigawatt. So in terms of HVDC, they probably don't really tell you that how big it is in terms of market, because you need the building, you need the transformers, you need the HVDC lines. So in terms of market, it is much bigger than the 30 gigawatt would indicate. Now, when we look at power electronics, we sort of have three major areas. I mean, we have control, we have topologies, and we have materials or the physics or the components as such, packaging, magnetics, and so on. When you look at the history, then over time, then the thyristor, so a device you can turn on, but you can't turn it off. That's from the 1950s. Then the gate turn off thyristors were done in the 1960s, 1970s. But the big breakthrough, big push came when the silicon-based insulated gate bipolar transistors, the IGBTs, were developed in the 1980s. So those are devices you can turn on and you can turn off, and you can operate at relatively high switching frequencies at relatively high currents. So we're talking here about kilohertz switching frequency and kiloamp currents that they can commutate. So that was a game changer and has really pushed power electronics very much forward. Nowadays, the talk is all about wide bandgap semiconductors, so silicon carbide, gallium nitride, and so on. So they are not yet used in the high power domain, but one could imagine that in a few years they might also move into that domain. When we look into the topologies, so topology is how do you put the semiconductors and the inductors and the diodes, how do you put these devices all together? So in the 1950s, it was the two-level converter, three-phase. Then in the 1980s, the three-level, the neutral point clamp converter was developed. So you went from two switching levels, plus and minus 1 to 3, plus 0 and minus 1. So you can have much higher, you can effectively have twice the voltage and hence twice the power. And then in the early 2000s, Professor Marquardt invented the modular multi-level converter, where you can have any number of voltage levels. So you series connect any number of modules in series. And that was a game changer and now dominates the high voltage power converters. Think of HVDC, for example. And then there's control. So control, I would say, includes modulation. The pulse width modulation concept from Black is from 1953, I believe. Hasse and Blaschke came up with field-oriented control. So that allowed us to control in AC machine, almost like a DC machine, by controlling DC quantities in a rotating reference frame, one for the D-axis and one for the Q-axis. So we get this nice decoupling. Takahashi and Noguchi came up with direct torque control in the mid-1980s. So we have upper and lower hysteresis bounds on our torque and our flux. It's a very, very fast, very precise control method. And then since the early mid-2000s, it's all about model predictive control. And I will talk about that in a second. So let's look into control and modulation. And let's really look at a very simple control problem. So let's just assume we have here a single phase converter, let's say 3 levels, and it's meant to control a current through an active RL load. So small ohmic resistance, some inductance, maybe 20%, and a voltage against which we work. Could be the grid, could be the voltage in the machine, a back EMF. So we want to regulate our current along this reference. Quantities with a star are a reference. And we do that by comparing the measured current with a reference current and then have a controller. And the controller would manipulate a reference converter voltage. And that would be sinusoidal at steady state. So of the same frequency as the current. But we have a converter, so we need to come up with switching. So we need to translate the continuous, the real valued reference signal into a switching signal. And the simplest way to do that is to use carriers. And because we have a 3-level converter here, we need 2 carriers, one in the upper half and one in the lower half. And whenever the modulating signal intersects with a carrier signal, we will switch down or we will switch up. So by doing that, you can see that we can nicely approximate, relatively nicely approximate the reference signal with the discrete valued switching signal using pulse width modulation. So we modulate the width of these pulses. So important is that we use feedback. So we compare the current with the reference current. So with that, we can stabilize unstable processes. We can reject disturbances. Think of a strong ripple on the DC link, for example, or us not knowing exactly what that impedance or that voltage is. Now, when we look at the classic control modulation methods we have, and we try to classify them a little bit. So one metric could be how high are the distortions for the switching frequency. So we have seen early on that we have this constant, and this constant is modulation scheme specific. And the other axis could be how quickly can the controller react? What is its bandwidth? What is its dynamics? So what is typically used today is field-oriented control or voltage-oriented control on the grid side is a classic pulse width modulator, carrier-based pulse width modulator or space vector modulation. It's relatively fast, but it also gives relatively high distortions. You could go for direct torque control or direct power control on the grid side. That is a bit faster, but maybe also leads to slightly higher distortions for the same switching frequency. The other extreme are optimized pulse patterns, and I will introduce them in a moment. So they minimize the distortions per switching frequency. So they sit here at the bottom, but we typically struggled to control them in a dynamic or in a fast way. So they're usually very slow. So we use a very slow way to control them. It's called scalar control. In contrast to these two methods, which are vector control, where I control torque and flux. Here, I just control the amplitude of my voltage, and I impose the speed, the fundamental frequency. Now, the question is, can we combine both? Can we find methods that sit here that are very fast, but also have very low distortions? And that brings us to model predictive control. Now, what is MPC? So the concept really is to use a mathematical model of the process, so your machine or your converter, to predict how it will behave in the future over a certain horizon. Could be a few milliseconds. And by doing that, you take constraints into account, constraints on voltages and currents. And you then determine the best possible control input, the best possible manipulated variable you're going to apply by solving a mathematical optimization problem. And in the next step, you obtain new measurements and you replan over a shifted or receding horizon. So let's look at the features of each of those elements. So the first one is the model. So we have a model of our system. That could be a state space model, maybe a nonlinear state space model, but in almost all cases, it is discrete time. So we work with discrete time instances k. In time step k, k plus 1, k plus 2, we have a sampling interval in between. And with this, if we now assume a tentative sequence of control inputs that we would apply to our converter, we can now predict what the future states, currents, voltages, speeds are going to be, and determine what the future outputs are going to be. So the quantities we're interested in, the quantities we want to control. And so this is sort of makes the controller smart. It allows us to make predictions, to look ahead into the future. The second step are then these constraints. We can impose limits on any quantity you want to limit. That could be inputs, so your modulating signal, your switch positions. It could be state variables, currents and voltages, or the variables you actually control. And these constraints, they're included in the design of the controller, not afterwards. So you will tell your controller that the current, for example, has to be limited. It must not exceed a certain limit. Because if you exceeded this limit, then at some point you would trip. And this is not done in a sort of anti-wind-up fashion after the PI controller. You tell your controller, and your controller will only try to come up with control inputs that ensure that over the next few steps, your state variables stay within these constraints. And then you need to map your objectives, your control objectives, into a so-called cost function. And that's shown, for example, here. For example, you want to track that certain states are close to their references. And you could penalize the predicted deviation of states from their references quadratically. So this is the 2 norm. So just the difference squared. So the squared 2 norm. And that's effectively the controller design of the tuning. And then we have numerical optimization. So we want to minimize our cost function. The cost function could be represented by these level sets. So at each sequence of inputs that you're going to apply, the cost has the same value. And you try to find the inputs you're going to apply that have the minimum cost. So you try to move as close as possible to the minimum. But we have seen we have these constraints, so we have these limits we impose, and they effectively, if we impose straight lines, they lead to this polytopic constraint. So our search space is limited, and we may only look for solutions within this polyhedron one. So this is numerical optimization. You can't analytically compute the minimum here. You go down till you hit these constraints. You have to do it with a somewhat, trial and error. I mean, those are sophisticated algorithms, but they run iteratively. So this would give you the optimal control input. And then we have receding horizon policy. That means you come up with a tentative sequence of control inputs that minimize your cost function over the horizon, but you will only apply the first control action. So only the first step. And then at the next time step, k plus 1, you will take new measurements or estimates, and you will do the same over the so-called shifted or receding horizon. So you're not going to apply the whole sequence and then optimize again here. And the reason simply is twofold. First, if you have a disturbance that you have not modeled, then you want to be able to react already here, because the disturbance would manifest itself in the measurements. Or if you have a step change in references, then you also want to be able to react already here. So this is a little bit like playing chess. You will also, in your head, come up with a certain sequence of moves, but you're only going to apply the first one. And depending on what your opponent chooses to do, you might adapt your strategy. You will not blindly follow through, regardless of what your opponent does. So you need to be able to react to disturbances, but you do want to have a plan. You don't want to just look one step ahead. And the same applies to MPC. A longer plan is beneficial, but to get feedback and robustness, you're going to apply only the first step. Now, let's go a little bit more into the details. And let's look into one method, and that would be model predictive control of optimized pulse patterns. What are optimized pulse patterns? So the objective here is to minimize the current distortions for a given switching frequency. And the switching frequency is effectively the number of transitions I have, say over 90 degrees, when my fundamental component is of a certain frequency. So this could be a 50 Hertz component, 2 transitions, 3-level converter. Each switch would have a switching frequency of 100 Hertz. So I want to compute these optimal switching angles that minimize the current distortions. And to do that, I assume I have an inductive load. But then I can analytically compute the harmonic spectrum of the switching waveform. I know it's inductive, so it's a first order system. And then I can minimize a cost function that represents the harmonic distortions and come up with the minimum, and that would be these 2 switching angles. And they give you this fundamental component. It's not a nice approximation, but if you have only 2 angles available, this is the best possible approximation that gives you the minimal distortions. Now, if you change the voltage of the waveform you want to produce, so for example, if you want to go up a little bit, then you need to change these switching angles. And you see the second one here would then move quite a bit to the right-hand side. This one would move a little bit, but by doing that, you would increase this volt second area. And you could then imagine that this fundamental component comes up. So if we look a bit more into this again, that would be the cost function you have to minimize. And that would be the cost. So first switching angle, second switching angle, and you see this is a difficult optimization problem. You have these hills and these valleys. So you can imagine that if you start somewhere, you might get trapped in a local minimum. We also want to achieve the desired amplitude of our voltage. So that's called the modulation index. In this case, it's around 0.8. So if you start here and you go down along this line, you will find the minimum. But if you started here and you walk down along the line, you would find a local minimum, not the global minimum. So you will need lots of initial conditions, and you will need smart algorithms that if you now have 20 angles and not 2 angles, that you come up with a solution that is close to the optimum. So it's a difficult problem to solve. Let's assume we have solved it. And now we want to control these OPPs. What you do is you take this switching pattern, you integrate it up, you multiply this half the DC link voltage, and that gives you a trajectory for your state of flux. So the integral of a voltage is a flux. And because we're interested in this case, controlling a machine, we're interested in the voltage at the machine terminals, and that's the stator. And what we did here is we neglected the fact that there's a stator resistance. So let's assume it's 0. But then you get this state of flux trajectory. And given the switching frequency we have, it should be a circle. It looks pretty bad, but that's actually the best possible trajectory there is, because it leads to the smallest possible current distortions. So that's something you want to track. You want to follow this trajectory, because when you do, you minimize your current distortions. for this given switching frequency. And how can you follow it? Well, you can change the times when you switch. So if you have a switching transition in this phase A here from 1 to 0, for example, nominal transition would be here. If you delay this a little bit, then you add this voltage times time, so this volt second increment. And the volt second increment is just a correction to our state of flux. So by doing these modifications, you can then change the state of flux in this A dimension. And you can do the same in phase B and C. So phase B would be in that direction and phase C in that direction. By doing that, I can accurately control my state of flux along this trajectory. So how do we design and model predictive controller? We know where we would like to be, so the reference of the state of flux. And we work here on these stationary orthogonal coordinates for alpha, beta. And I have estimated my state of flux, and that gives me an error. And let's assume this error, I take the two norms, I take the error in alpha squared plus in beta squared, and I take the square root. And this error would be high initially. Now, this is the time axis. This is where I am, and I would like to reduce this error over this interval, which is my prediction horizon. And whenever I have a switching transition coming up, for example, in phase A, then I can modify them, and I modify them such that I reduce this error. And I want to minimize the predicted error at the end of the interval by making these modifications. And I want to modify my pulse pattern as little as possible. So I have an error now. I have a disturbance maybe now, which I don't know about, so I ignore it. So I can't model it. And I have a correction now, and that gives me the predicted error at the next time step. So that means the error I have now minus all the corrections I'm going to make over the horizon of n steps. I can predict what my error is going to be at the end of the horizon, indicated by n. N is the length of the prediction horizon. And the corrections are simply the modifications in time. So these delta t's, delta t A1, phase A, the first one, phase A, the second one. And delta U is the time step, is the switching transition. It's either 1 or -1. So here it's -1 and here it's +1. So it's just a sign. And I sum them all up, go from A, B, C into alpha, beta, multiply with half the DC link voltage. So then these are volt second corrections in alpha, beta. So I have my manipulated variable are these corrections of the time, and my controlled variable is the state of flux error. So I have a cost function where I minimize the predicted error or the uncompensated error at the end of the horizon, and I also want to minimize the changes in the switching instances. Now let's have a look at a little animation here. So this is for a variable speed drive. You see here the fluxes in alpha and in beta axis. You see here the red line is the state of flux reference trajectory. You have as the shorter flux is the rotor flux, the longer one is the state of flux, and we would like to bring the state of flux onto the new reference. And we are increasing here the torque. We are at high speed. This is difficult. We have very little voltage available, but you see here the future. I mean, the predicted torque. Torque is around 1 per unit, so 100%. And everything here is the past. And down here you have the switch position. So phase A, B, and C. This is the past. This is the future. Dash dotted line are the predictions over the horizon, and these dotted ones, those are the nominal optimized pulse pattern. So you see, when we operate here, there may be made small modifications to the switching instance, but they're small. And now we get a torque step. We have relatively high torque, 100%. We want to bring this torque to 0. That means the state of flux has to be on top of the rotor flux. we insert here a negative pulse. Didn't exist in the OPP. We drive the state of flux vector back until it's on the rotor flux, and we have 0 torque. And then let's assume we have a torque step back up from 0 to 1. There's very little voltage available, but you will see that huge corrections are being made. Now we have the step. Big corrections are being made to the pulse pattern. So all these additional volt seconds, which we don't need, we remove. So it's physically not possible to move it more quickly up. Okay, so that's model predictive pulse pattern control. If we use that in the lab, in the medium voltage lab, you have here a machine, 2 megavolt ampere machine with the cooling on top, water cooled. You have the converter. And if we now compare this model predictive pulse pattern control with direct torque control, you see here the currents. This part here is zoomed in. You see that MP3C has much lower current ripple. The fundamental component is the same. The ripple is much smaller. And the switching frequency is also a bit lower. So we reduce the current distortions by around 50% for the same switching frequency compared to an established method. If we apply torque steps, then, I mean, the blue one would be the old method, and the predictive method would be the red or the yellow one, depending on the switching frequency. You see that the time it takes till you hit the new reference is exactly the same. It's around a millisecond. So the dynamic performance is similar to the established method, which was considered to be the fastest possible. So one could then claim that this MP3C, model predictive pulse pattern control, sort of squares the circle by combining the benefits of direct torque control in terms of dynamic performance with the steady state performance of optimized pulse patterns. Now, what is that good for? I mean, with a drive or a converter, where we want to drive a machine at a certain frequency electrically, as we go up in the electrical frequency, we have to go up in terms of switching frequency of our converter if we want to achieve a certain power. And at some point, our switching frequency gets so high that we have to reduce the current that we can carry in order to achieve acceptable current distortions. So this is called derating. Now with MP3C, we can reduce the current ripple. So that means we can increase the current. We reduce the switching frequency, so we can increase the current, and we can increase the voltage a bit. So we get a few percent more power at low speeds. But this derating point happens much later because we can achieve the same harmonic distortions at a lower switching frequency. So the derating kicks in much later. And these are new, I mean, the green area is effectively money, if you want. So you get more money for the same hardware, which is nice here, but it really pays out at these higher fundamental frequencies. So there's a nice cost reduction to be achieved. So a few conclusions about MP3C, model predictive pulse pattern control. One is we minimize the harmonic distortions in the load. We can meet grid codes, harmonic grid codes. We can reduce converter derating, as you have seen. It is simple to solve online because the majority of the problem has been solved offline during a long weekend when we compute these optimized pulse patterns. And it's a simple and general method. So you can pretty much use it for most converters, particularly in the medium voltage domain. Here you see an example of a three-phase, single-phase railway intertie from 50 Hertz to 16 2/3. This is a matrix modular multi-level converter. So you can also use it for that. So now challenges are, people say optimized pulse patterns, they're only available for low pulse numbers, so low switching frequency per fundamental frequency. But there's ongoing work to compute them for very, very high pulse numbers. So this one here would be 10 kilohertz switching frequency at 50 Hertz fundamental. Pulse number 100. And if you want to go to anything beyond an inductive load, where you have filters, you have a more complex system to consider, but you can compute them as well. Now, before I wrap up, I have a few slides on converters that start dominating power systems, and I want to give you a little bit of a flavor of what sort of problems that could arise. So let's move from drives to offshore wind farms. This is one that was built in 2010, 2011 in the North Sea. Those are 5 megawatt wind turbines, so-called doubly fed induction generators. So there are 80 of them, and they are arranged in 4 groups. So wind turbine group A, B, and C, connected via transformers with cables to a so-called point of common coupling. So this is offshore, somewhere in the North Sea, so off the Netherlands. And now you have a 2 kilometer long DC cable at 150, I believe, kilovolt to bring that power of 400 megawatt to the shore. So you need an HVDC converter station. And this one was the first HVDC converter station linking an offshore wind farm to the onshore grid. And being the first one is always interesting because things can happen others have not yet experienced because you're the first one to experience it. So this is what this HVDC converter platform looks like. It's called Bovin Alpha. It's a massive construction. You have this point of common coupling, filters, converter transformers, another filter, phase reactor, and then here the converter going from AC to DC, and then here the DC cable on the ground to shore. Now what happened is that as more and more of these wind turbines were commissioned, that large voltage harmonics started to occur at certain operating points at the point of common coupling. So we're talking here about more than 100 kilovolt AC with a voltage GHD exceeding 20%. So that's crazy. And as a result, these filter bank here experienced large harmonic currents and had huge overloads and experienced damages. Now the question was, what happened? So this went through the news. I mean, a task force was created and people got a little bit worried that operating effectively all offshore wind turbine projects were put on hold because this problem was not understood and it wasn't clear how to resolve it. Now, when you do a harmonic analysis and you model the system in detail, you have here the frequency and you have here the gain from a wind turbine from a certain voltage harmonic to the current it drives in the filter. And you see that at certain frequencies, a couple of 100 hertz, you will get a spike. So that means if the wind turbine injects a harmonic at this point here, it will drive a significant harmonic current in the filter bank. So that's something that became clear. What also became clear is that the biggest player is the HVDC converter. It's not that the HVDC converter caused the problems, but it's by far the biggest player. So it's maybe good for the HVDC converter to try to actively do something about it. So we came up with a way to dampen these resonances actively using the converter. And if we did that, then we were able to bring down these transfer functions. So effectively remove these resonances and remove the large currents in the filter banks. So there's a rapid growth of converters in the grid. PV, solar farms, HVDC, offshore wind. A converter, traditionally the way it's designed, you assume it's connected to a stiff grid rather than a weak grid, or rather than a grid that is formed by other power converters. You have lots of sources that can lead to resonances. So think of the system here. You have inductances, capacitors, inductances and capacitors, inductances, capacitors, and so on. And you have players injecting harmonics. So, and you have, because it's medium voltage and high voltage, you have very, very, very little ohmic damping. And challenge is really to ensure interoperability and stability. And standards are now being developed to make sure that such issues do not happen again. Now let me conclude. I have 2 slides left. I think the timing is pretty good now. So when we now take a step back and we look at the bigger picture in power electronics, what we see is that the power electronics market is maturing. So there's strong competition, there's smaller margins, and there's commoditization. That means it is difficult to distinguish between some of the products, because all the products or many products in certain segments do the same thing. And then the only differentiator is cost, price, and that drives down the margins. On the other hand, power electronics is a key technology. I mean, you've seen how abundant it is. It's now revolutionizing transportation. Think about cars, maybe planes will be next. So it's a key ingredient to achieve a carbon-free society. So to mitigate or to reduce the impact of climate change. What we also see is that the demand for high power and high voltage is ever increasing. So we increase the voltage in order to increase the power. So we see that in offshore wind, in wind, for example, the bigger, the better, because it brings down cost, because a large of the cost of offshore wind is driven by the foundations and the installation. So if you have a wind turbine that is 20, 30% bigger, then your installation and foundation cost goes up just a little bit, but you get 20% more power from it. HVDC is now in the range of 10 gigawatt, prices are getting ever bigger. And then there is digitalization. So we're collecting data, big data, and we're starting to analyze this data. We're starting to do predictive maintenance. We're starting to offer services that can make good use of this data. And I mean, it's not artificial intelligence, but it's using data and taking advantage of it. Computational power and computation bandwidth are available in abundance. So we still have this Moore's law, doubling computational power every 18 months, and we can communicate seamlessly and reliably. And we have performance requirements that are increasing. So think of new IEEE efficiency standards now being applied to electrical machines, and also grid standards in terms of harmonics. But that brings us to something one could call the smart power converter. So a converter that achieves a higher system efficiency by reducing the losses in the system. So this we have seen a little bit. You can use optimized pulse patterns for that, for example. So you switch less, you reduce the losses, the switching losses, you achieve the same power. Or you can try to increase the power actually for the same converter hardware. And that is highly, highly beneficial because you can save a lot of cost. You also want to increase the availability of your system. You want to avoid outages, nuisance outages. You want to make sure that when there are disturbances and faults, that you don't trip, that you can keep operating. And then there is this plug and play operation, microgrid ready. That's hard, but what you want is effectively that you just add here converters and they don't interfere with others and they play nicely with them. Because what happens as you add more and more to them, you change the total system characteristics. So you don't want to redesign the system when you add more and more of them. So my last slide, conclusions, commercial benefits of modern control. We have talked, it's smaller size, weight and cost, better performance, stable operation. Now, whenever you introduce something new in industry, you have challenges you might not have thought about. And one of them is you need to build up a lot of know-how. You need to educate people. They need to understand. You need to educate R&D, sales, the commissioning people, the field service engineers. And in order to facilitate that, you need simplicity. So you need to have a concept that is as simple and easy to understand as possible. And it needs to be applicable to all your products. I mean, it doesn't make much sense to have one specific method that you can only use for one specific market segment. You need to have a method you can use for drives, synchronous machines, asynchronous machines, permanent magnet synchronous machines, grid connected converters, static frequency converters, wind, metals, marine. You need to have it applicable to the whole range. But industry interest is ramping up. I mean, we're having first products. This is a load commutated inverter here in Kolsnes in Norway with improved low voltage right through. We have this model predictive pulse pattern control now being a commercial product. There is significant interest in the academic power electronics community. So when you look at the number of publications, new publications per year on IEEE Explore, so I take a year and I count the number of publications that have predictive control, converter or inverter. And then you see that every 3 years, the number of new publications doubles. So if you had here 100 publications in the year 2010, 3 years later, we have 200, and then 400, and then maybe 800. But not all proposed methods have a tangible benefit. And in order to get industry interested, you need to have a convincing story how money can be saved. So you need to clarify what the significant monetary benefit is, because for industry to introduce a new method, this will cost them tens of millions of dollars. So in order to warrant this upfront investment, you need to have a very convincing story how you're going to save a lot more money than the investment of a couple of tens of millions of US dollars. So having said that, I would say we are still at a relatively early stage when it comes to modern control. I use that, I think it's encouraging for the younger people. Sometimes you look at it and you think everything has been done. I would say we see only the tip of the iceberg, and there's a lot more to be done and to be discovered. So if you're more interested in the topic, there's a little book that's now 4 years old. Feel free to have a look at it. Maybe it's available in your library. So with this, I would like to thank you. Thank you very much to you for listening. I mean, I think it's a record number of participants. It's a great honor to talk to you. And thanks, Professor Mahesh and Professor Vinod Kumar, for having set that up and for hosting me today. Thank you.
Thank you, sir. Thank you. Some of the participants raised a question in your presentation. Does this MPC technique will need complex digital processor unit?
No, there is very little processor unit needed. We have a very simple one. It's nothing fancy. It is not more computationally expensive. The trick is that the problem has been solved offline. We only modify a little bit here the switching transition. That's cheap. Other questions?
Any other questions by the participants?
Do any participants have any?
Actually, I have one question. Hello, yeah, this is Siddharth here. Sir, when you are saying you change the switching pattern, so it means you are changing the modulation signal, right?
Yeah, I should have added a block diagram. I'm not sure I have it in here. I mean, the answer is no. I mean, the answer is no. I mean, what happens is that you decide on you decide on the modulation index, but your controller will push the switching instances around. I mean, the controller does not change the modulation index in the phase. The controller moves these switching instances around.
But how do we move that pattern? Means, because if you're not changing the modulation or the carrier, because then this pattern is fixed, but how do you move it? And according to what, there must be some signal which tracks and then it moves.
Yes. I would have to find another presentation quickly. Would have to think quickly. Should have anticipated that and had prepared a backup, but I'm almost there. Let's see. No, there's also none. No, I mean, what we do is we ask ourselves, where's the rotor flux and what is our torque reference? And based on rotor flux and torque reference, you can compute the position of your stator flux. And you know your speed of your machine and you know the flux magnitude. That tells you, and you know the DC link voltage. That tells you the modulation index you want to have. And the fundamental frequency and the desired switching frequency tells you the pulse number. So the switching frequency. So then you load the optimized pulse pattern. You have offline integrated up the stator flux trajectory. You've computed this trajectory for each pulse pattern. The magnitude is 1, unless you do field weakening. And the position you get where you would like your stator flux to be, you get from the rotor flux and the torque. And now you need to control your stator flux to that reference point. And this you do by changing the time when you switch a little bit. But if you now, for example, have a DC link voltage ripple, what you do is you change the switching transitions, but you do not change the modulation index. You only change the modulation index when your speed changes a lot. But when your torque, for example, changes, has a step change, you still use the same modulation index. And during a transient, like here, when you have a torque step, your modulation index is always the same. That MP3C gets, but MP3C will play with the switching instances. Okay.
Okay. So what I understand is maybe when you change when there is a comparison to the reference and the actual signal, there is a change in the switch, and maybe that changes the modulation. So I think in that way we are just tracking the flux with the changes.
Yes. Yes. The modulation index is a static quantity that effectively tells you at steady state what the voltage would be that your drive would get. Think about it like that. We have the inverter, we have the machine, we measure the currents. So we have some observer for our flux. So we will determine where the stator flux is and where the rotor flux is in alpha beta. And then we have a speed controller, absolutely classic, that gives us a torque reference. We have a torque controller that compares the estimated torque with the measured with the reference torque. It tells us what is the angle between rotor flux and where the stator flux should be. And given the position, the angular position of the rotor flux and the load angle, I can compute where the stator flux angle should be. This is shown here. Rotor flux estimated, desired angle that is proportional to the torque tells us the stator flux should be here. Now I need to find the stator flux reference on that trajectory, because this trajectory encodes the optimal current ripple. And then I drive my stator flux to that reference by modifying the switching instances over a certain horizon. But you see here that I will not change the modulation index a priori. I will work with the optimized pulse pattern I received, but I will not change now the modulation index a priori. I might, for a few milliseconds, change it, but this is done implicitly. Okay.
Okay, I got it. So do we have some example for grid tie inverter? Anything means not motor, maybe some grid tied inverter where some fluctuation on the grid side and then accordingly the.
Yes, maybe this one here, where you have a grid connected converter. Here it's trying to draw current and it has an LC filter. So this would be the capacitor and this is the filter, the L, and then we would have here the transformer leakage. And that would be the point of common coupling. Now you do exactly the same thing, it's just that this controller would control not the speed, but the DC link power. So you would have the DC link voltage reference, the measured DC link voltage coming from your converter. That tells you the power you should draw, the active power. You control your reactive power, and you do that by changing the amplitude of your voltage, so maybe your modulation index. And the active power tells you what is the angle between the grid flux and your virtual converter flux. So this one here works with virtual fluxes. And then you use the same principle. Plus maybe some active damping loop that we inject here this delta flux active front end to add damping for this LCL structure.
Yeah, okay, I got it.
Sir, one more query.
But it's not
how do
published.
we
I don't
overcome?
think we have publication about it.
Okay. How do we overcome the problems faced by internal capacitance of thyristor in the converters?
Say again, please. How do we work on the problem?
How do we overcome the problems faced by internal capacitance of thyristor in the converters? Internal capacitance.
Internal capacitance of the thyristor?
Converter.
The internal capacitance of the thyristor. Yeah, I mean, here we have gate commutated thyristors. So these are devices you can turn off, but you need a strong gate driver that is integrated. So it is part of the package. It is right next to the semiconductor. I think I have one here. So that's what they look like. So you have the semiconductor here on top. So I don't know, 91 what is that, millimeter. And then you have here the gate driver. So you need to store a lot of energy. And when you want to turn the thing off, you need to flush the carriers into the semiconductor to commutate the current away. So this thing would, commutate 4 kiloamps and would block, you can see it here by looking at the diameter, would block 4.5 kilovolt.
Thank you, sir. Thank you. No more queries. Now I
Any further
request.
question?
Now I request Ms. Naira, IEEE PELS Vice of New Horizon College of Engineering, to give vote of thanks.
Thank you, sir. Good evening, sir. Thank you so much for this really insightful session on controlling megawatts with power electronics. This session was amazing and gave us all really good knowledge on this topic, and I hope every one of us here can agree on that. I would also like to thank the New Horizon College of Engineering and the Electrical and Electronics Department, NHCE. Special thanks to our principal, Manjunath sir, HOD of IEEE, Dr. Mahesh sir, and our branch advisor, Dr. Vinod Kumar sir, for giving us this opportunity in organizing this event. Lastly, I would like to thank all the participants for their support throughout the session and taking their time off to attend this webinar conducted by IEEE Power Electronics Student Chapter NHC. Thank you, sir.
Thank you very much. No, it was a pleasure to talk to you. I've never had 170 people, so
okay.
Thank you very much.
Thank you, sir. Thank you.
And feel free if you have questions or comments, just send me an email. I will try to reply, okay? Or if you have ideas or, I'm happy to discuss, okay?
Okay, sir, okay. Thank you. Thank you, sir. Thank you.